ahead and get started. This is USGS Hydrography Advisory Call. This is Al Ray. We've also got Becky Anderson on the line. We don't have a whole lot to announce today, except that the Hawaii data for NHD Plus high-res is now available. So if you are interested in NHD Plus high-res for Hawaii, then it is done and available on our website now. And so today we've got Dave Blodgett, who is in the USGS Water Mission Area, and he's going to give us a presentation about a number of different things. I'll let Dave go ahead and take it and introduce his topic and himself. So go ahead, Dave.
All right. So is my audio good for everybody?
Yeah, it sounds good.
All right, great. All right. Well, thanks for having me, Al. As Al said, I'm with the USGS Water Mission Area. I'm part of a geospatial intelligence group, our integrated modeling and prediction division.
Dave, hang on just a second. Your sound just went. We've got an echo here. I'm going to try muting everyone again and unmute you. Okay, Dave?
Okay.
Okay, Dave, I think let's try it again.
All right. Is that okay?
Yes, that's better. Thanks.
Great. All right. So yeah, as I was saying, I'm with our geospatial intelligence branch within an integrated modeling and prediction division. I've been working in various kind of venues on work related to this for quite some time. One of the major motivations has been to identify the relationship between the NHD and the WBD. And that's been driven largely by work that we've been doing for the National Water Census, things that were motivated by the Secure Water Act to deliver water availability information, so water budget information attributed to 12-digit hydrologic unit code watersheds. So the quest that I've been on in this space has led me down a number of interesting avenues, one of which was helping to get a data model for hydrographic features or hydrologic features published through the Open Geospatial Consortium, and then various other kind of national modeling efforts that I've been engaged with have had impacts here. I did a detail at the National Water Center working on the National Water Model, and a lot of the software development that was done for this project was done while I was there on detail, thinking about the kind of geospatial framework for that model. And more recently, I've been working directly with the USGS's National Hydrologic Model. So the distinction there is that water model is an hourly model, hydrologic model is a daily model. Basically working toward having operational capacity for hydrologic modeling at a variety of scales that's supported by this kind of solid basis of hydrographic and hydrologic features. So what I'm going to present to you today is some work that is currently in review. So take it for what it is. It's been worked for a while and is in pretty good shape, but the manuscript is in review and final. So that's kind of the status of it. I'll go ahead and jump in. PowerPoint in focus here. All right. So the premise we're starting from, or where we kind of went here, is that there's this dual concept of drainage basin and mainstem that are really kind of an organizing principle for hydrologic landscapes. And so I did a fairly deep dive into literature and definitions going back as far as I could. And found some really interesting work from kind of early quantitative hydrology. This graphic in particular is from, I don't actually have it on the slide, the date, but anyways, it's from, gosh, I want to say the 1600s, where this this is the first diagram I could find that showed a drainage basin. So the dotted line there ostensibly is the drainage basin for the Seine upstream of Paris. And what I found really interesting here is that the Seine source is the name of a town, actually. So there's a town in the headwaters of the Seine called Seine Source. And I'm not sure exactly how long that name goes back, but presumably people, in this part of the world knew that the Seine was the main river in this drainage basin. And it was in some ways identified as the main river in this network over time. And this got me thinking, that going back even further, how did people decide upstream Mainstem before we even knew the concept of drainage basin? I mean, before people recognized that there was a basin upstream of a place on a river, there was really no concept that a river had a source that was this area, and the rain in the area generated the flow. There were all kinds of crazy theories about what created rivers and how rivers grew down as you go downstream. So anyways, there's a lot to look at there historically of kind of how these notions and how these concepts evolved. But I really like this graphic as kind of a very early days where this comes from. Okay, so I've alluded a little bit to kind of one of the basic issues we've identified, and this is just some these are a couple of key sentences from the introductory material of the paper that we've got in review. And I've highlighted some of the important pieces here. So I found a great reference book, Fluvial Hydrosystems from 1996 by this gentleman Petz. And in that, he describes a drainage basin in a really nice way. So, this idea that a contributing area as a basic hydrologic unit of the landscape. And the quote is that it encompasses a cascading system of connected hill slope and channel subsystems. So I would say the hill slope and channel subsystems are essentially catchments, and a drainage basin is a cascading system of catchments, and it's a total contributing area, right? If you look at Wikipedia for drainage basin or watershed, drainage basin is kind of the root word that you come up with. If you look in multiple languages, drainage basin is a fairly direct translation, say in German, to what we mean when we say the contributing area upstream of a place on a river, and that's helpful. I think very very precise terminology for this general concept is important. So we've kind of run with this drainage basin term rather than say watershed. The reason for that, watershed is actually defined, say in German, as the actual line that encompasses like the what we might call a continental divide, right? The watershed is that thing, the line on the landscape that divides two watersheds or two drainage basins. So going a little further, we recognize that rivers have a drainage basin upstream of a given location. This is just kind of a general thing that we understand to be true, right? But to add to that, we also kind of recognize that there is one main river in that drainage basin, and that one main river is determined through various historical artifacts of what people thought was the main river. It's not the longest. It's not necessarily the longest. It's not necessarily the biggest. Many times it's just an arbitrary societal determination of a name, or whatever it is, right? It's a mishmash of fluvial geomorphic characteristics, hydrology, climatology potentially, depending how big the river is, et cetera, right? And that's fascinating to me. It's because this isn't a strictly physical determination, what is upstream Mainstem. And so all of that kind of leads to this, all of the kind of long-held understanding of what a drainage basin is, that rivers have upstream Mainstem. That leads to, these kind of really intuitive properties, having a very vague and kind of general understanding of them when we start to talk about them in technical literature, for example. So where that's led us is that a lot of the kind of the data or the research, engineering reports of sorts, they reference these landscape features, drainage basins, rivers, etc., using loosely defined language that's kind of vague. And that's a problem. We have a hard time finding, say, all the literature on a particular topic for a particular river. It's not as easy as it ought to be, right? And we even have a hard time, say, translating where our stream gauges are on rivers from one data set to the next. And I go back to this issue of kind of a general vagueness to how these features are defined for why we have so much difficulty with this. So that's a little bit of kind of the background, or maybe a lot of the background. See, it's already 12:15. So we're now in a position that this hydrologic features standard is out. It's a standard for surface features that kind of recognizes its role in a surface water framework. There's ongoing and future work to be done to relate it to groundwater, but for now we've got a lot to do in surface water. And so HY features is organized into kind of two. There's a duality in HY features. There's this general notion of a catchment, which is a thing that accumulates rain, delivers it to waterways, and conveys that water from upstream catchments to downstream. So a catchment is this very holistic thing that has a dual role of getting water to water bodies as well as accumulating flow in downstream direction, kind of into hydrologic networks. And then this idea of a hydrologic nexus, which is the interface between catchments, the place that, say, two units of a hydrologic model might interact, or a place that we might want to break up our network because there's a dam, right? The hydrologic nexus is a ostensibly zero-dimensional feature, but it's the place where things combine, things interact. So we, in this Mainstem's work, which is what it's come to be called, this drainage basin and Mainstems, we are seeking to use these concepts of catchment and nexus as a conceptual model, and basically applying those concepts with a little bit of refined logic. And the refined logic is this idea of drainage basin and Mainstem. So the questions we were asking in the work is really at the heart of it is can the paired concepts of drainage basin and Mainstem be used to integrate multiple hydrographic data sets and to support kind of linear referencing, right? So linear referencing because we want to be able to catalog and index observational data, research, all kinds of information, assets that may be at risk from flooding, et cetera, and multiple hydrographic data sets because there's just this reality that we have lots of different realizations of hydrography across the landscape, and we need a way to get them all kind of working in the same general framework. So we wanted to define a very lightweight logical data model, but it needed to be able to handle very complex network and graph operations as well as indexing of data. And then there's this notion of hydrologic integration rather than just geographic integration that we raise in this manuscript and has really been brought up in a number of venues. And if you're familiar with the idea of place-based, being based on place rather than based on locality or geography, that's really what we're talking about here. We're talking about a river or a drainage basin as a place, a thing that has identity and may have lots of spatial representations. So what we're trying to get at is there a way to do hydrologic integration based on hydrologic identity rather than just geographic identity? Okay, so a little bit of review of some terms. We have this notion of incremental catchment. NHD Plus implements incremental catchments. They cover the landscape. They have a corresponding network, one internodal reach for each catchment, for the most part. And incremental catchments can make up drainage basins. And what's interesting is drainage basins because they're nested, because you can say, there's the Mississippi has the Ohio has the White has some creek. They nest. At the bottom level of that nesting, if you dissolve away all the boundaries, or you union all the boundaries together, you end up with incremental catchments. So that kind of set of nested drainage basins that then can kind of realize your incremental catchments, that's a very important aspect of this kind of logical data model. The next two here, headwater and outlet, it's essentially, I'm pointing those out because a drainage basin is ostensibly defined by an outlet and some headwater location, or a drainage basin and mainstem is defined by those 2 points. And probably the most important assumption that we made in this work was, in a given hydrographic data set, the headwater location should go to the same outlet. And if those 2 points don't join, if you don't have downstream mainstem as the same location, that is basically saying that these two data sets model hydrology differently. There may be a reason that one chooses the diverted path versus the main path differently, but those are the points. Those are the issues that we actually really do need to find and tease out to understand why our hydrographic data sets are modeling the hydrologic system differently. And the last one I have on here is getting a little bit technical, but I think it's very important to mention that this mainstem concept has really already been implemented in NHD+. It's stream level. Stream leveling, this method of determining upstream mainstem, is something that we've been doing since RF1, and we've recognized that there's this overriding identifier, and then a general geospatial or geomorphic rule that we use to determine what upstream mainstem is in the absence of an identifier. And for the most part, all we've really been doing with this work is exploring level path and stream level and applying it in slightly new and novel ways, and kind of applying some new workflows to combine data and find what we can do toward these goals. So, one of the biggest questions that we came up with in this work is, what is a headwater? And so this graphic is showing you, I believe this is, and it's not super critical. This is 3 hydrographic data sets. I believe that this is RF1, NHD plus medium res, and NHD plus high res. And the point here, I know red is RF1. And the point here is that red line is a first order stream from RF1. And the dark blue line is the main stem as indicated by, or the thick blue line is the main stem as indicated by NHD plus version 2. And the black lines are the full network as realized by NHD plus high res. And so why, for example, does RF1 not even have the main upstream extent that NHD plus version 2 does? I don't know. That's not all that important. The question is this whole area a headwater because RF1 only has one first order stream? Well, no, it's a headwater in RF1. The headwater in NHD plus medium res is something else, maybe up here, right? And in high res, which one of these is headwater? Maybe it's this one. Maybe it's the one that NHD plus version 2 chose. But I bring this up because it kind of makes the point that for integration, for hydrologic integration of these data sets, what the ultimate headwater in is actually defined by the resolution of the data set you're interested in. Downstream of the outlet of this RF1 is essentially the vaguest, the most vague definition of the headwater of this particular river. The outlet of the first order NHD plus high res stream upstream of where these things start to diverge is the most specific point representation of the headwater of this particular system. And we need to be able to recognize that and handle that. The direction I've been taking things, and I think at the scale of, say, the conterminous US, determining headwater 12-digit hydrologic unit code watersheds is a reasonable place to be. That encompasses most of the headwaters in RF1, for example. and that size from a, how big of a river comes out of a first order, or a zero order, depending on how you look at it, huck. That size it's a good general kind of landscape size to say those are our headwater areas. And any smaller than that, and things are just going to end up being kind of weird depending on the data set you look at. And those kinds of distinctions are really necessary if we're going to be able to make progress. Those kinds of simplifications are critical. So. Okay, so we did a number of case studies, and I'm going to move through these fairly rapidly, but the first case study that we illustrate in the paper is the Network Link Data Index. Many of you may have heard of this. Essentially, it's an implementation of level path network navigation using NHT Plus version 2 in a web API. So this is a system, you go in, you say, I want to start at that location on the network and go upstream Mainstem. It goes to NHT Plus version 2, navigates, and then goes and finds the things you're interested in along the way, whether those things are flow lines, catchments, a drainage basin, other indexed locations such as stream gauges or water quality sites. And it's fairly rudimentary in the sense that it only supports catchment indexing. It doesn't support reach code and measure directly, but it does represent the catchment network, and it does represent main stems and drainage basins, and exercises this notion of linked data, where you have observation locations linked to catchments that are then part of a main stem network. So this showed the utility of this. It shows some of the limits of this work quite well, but it certainly shows the power of having kind of drainage basins that are aggregations of incremental catchments and a main stem network that connects all that together. And then how you can connect that to observation locations is fairly clear. There's plenty more work to do in this space, though. The second case study was looking at outlet locations on one hydrologic geospatial fabric. In this case, one defined for the current version of the National Hydrologic Model, which was built on NHT Plus version 1, and trying to figure out where the known hydrologic unit code, 12-digit hydrologic unit code watershed outlets fall on that network. And the nuance with this was that we have these 12-digit hydrologic unit code watersheds on NHT Plus version 2. So the nuance here is it's very important to determine what I've started to call hydrologic similarity, not just geospatial similarity. And that's because we're trying to say what's the stream flow essentially at the outlet of a huck. And modeling stream flow requires hydrologic similarity, kind of watershed representation similarity. And that's a little bit different than, say, geospatial or visual similarity. So a couple of things we looked at were things like how far apart were these on the network in a linear way. And so these two diagrams are just showing some of the kind of outcomes of this work. And we certainly ended up with some tails, which is kind of inevitable in this kind of work. But yes, the idea here is these kinds of distributions allowed us to say, well, the ones that are within so many kilometers, essentially in linear distance, this is a distance between an existing model outlet, model pour point, and a 12-digit hydrologic unit code outlet. This allowed us to say, well, this certain set is close enough. We're just going to assume the stream flow doesn't change much between those 2 points. And this other set, we need to do something else. We need to do some area weighting. We need to determine how to estimate flow for these 12-digit huck outlets. And then this other one is a similar, but looking at drainage area. So kind of normalizing total drainage area to basically say, well, there are sets that are close enough together that we can assume the drainage areas are modeled the same, and there's another set where the drainage areas are modeled differently, and we need to do something, right? So this wasn't a panacea, but it was a very good case study, a very good way to evaluate how using this idea of Mainstem we could basically determine hydrologic similarity between one set of watershed outlets and another kind of pre-existing set of model unit outlets. Okay, so the third case study was working a little more specifically to compare the network of the 12-digit hydrologic unit code watershed network, so the 2-HUC coding of the HUC 12s to the NHD plus version 2 network. And this was somewhat to evaluate the quality or the hydrologic kind of integrity of the outlet locations that that Curtis Price actually established from NHD plus version 2 in the WBD. But just more generally, it was an opportunity to evaluate the 2-HUC codes and test this Mainstem paradigm. And so the graphic on the screen shows one of the really common situations we run into with the WBD. So the thin black line is a WBD boundary. The thicker blue lines are a river network, and the arrows kind of try to show the direction of flow. So it's very common that a tributary just barely comes into a HUC and then leaves. And the way that the WBD often models this is a unit that just barely enters and then leaves immediately is said to go into this one, so is said to go into the one on the left, and then the one on the left, the combined flow, goes out, which is literally true if you zoom way in on the geometry. But from a hydrologic point of view, from thinking of these HUCs as catchments maybe, that is not true. The HUC coming down from the top here contributes directly to whatever's down here, and the HUC on the left contributes directly to the one on the right. This is something that we can identify using kind of Mainstem logic and using process of elimination and Mainstems to essentially eliminate HUCs with this condition. I won't go into a lot of that. That's a fairly nuanced set of analyses that we did, and if you're curious about that and kind of how that all fell out, I'm happy to share more information about it offline. Just contact me. But this was really interesting work. What we found is, broadly speaking, the 2-HUC codes go where they're supposed to go, but there's some not small percentage that are they're not coded in a especially hydrologic way. We'll put it that way. They're not what a hydrologist would expect for the drainage areas to contribute to each other. Okay, so I believe this is my last case study. This one, I wanted to dig into NHD plus high-res and kind of see how this corresponded. So essentially took some NHD plus high-res data and attempted to track headwater locations to outlet locations between medium-res and high-res NHD plus. And just kind of did that for a large swath of the landscape and wanted to look at the metrics of what came from either end. And broadly speaking, they go where they're supposed to go, but there are outliers. And this was a great way to identify places that either the medium res network has some kind of downstream connectivity issues, or the high res network has some downstream connectivity issues. And as you watch this animation, you can see some places where there are definitely some main path kind of divergences in high res that are not present in medium res. And there are some places where things don't quite agree. But in general, they agree quite well, and the main stems, the big ones, are quite good. But there's definitely some kind of valuable QA/QC content from this analysis that we could apply to the high-res network going forward. Okay, last one, just for fun, I did this with RF1. I mentioned this, and people, RF1, what? Why did you go back there? And I was like, well, because it's interesting. And similar, I threw up this a second ago. We basically found that RF1 headwaters diverge, sometimes a lot earlier than you might expect. But by and large, the main stems, everything agrees. Once you get too far downstream, RF1 does some funny stuff with water bodies, but for the most part, this was a really valuable and kind of interesting piece of work because it verified that some of the core kind of big network pieces are intact and work the way they're supposed to. So, so I'm feeling pretty good about this. The outcome of this work is essentially a table that says, here's the headwater and the outlet for a given mainstem in all the data sets that I just listed. And as we work forward, we'll be able to have this essentially lookup table of mainstems that says, oh, you have something on that mainstem, we'll go get that path from that other data set if you want the same mainstem worth of data. And having this kind of general purpose mainstem-based crosswalk that obviously has these associated drainage basins can become a tool for us going forward. But we have these open questions. And I think the biggest one in my mind is this idea of when we say headwater, what do we mean? Where is this thing we call headwater? It's defined based on the resolution of the data you're looking at, and it's defined on how hard has it been raining lately, potentially. And this is really important for some of the conversations we have around Lotus right now. This where does the blue line start and why is a really nuanced question, and it's something that's becoming increasingly important. So that's my future work question one. So can we identify consistent and defensible logic for creation of a headwater? And this is something I in creation of NHD Plus version 2, for example, they did generate catchments upstream of the top end of a blue line, but those polygons weren't saved. I think that's a really interesting analysis. The what is the zero order catchment that contributes to either the top end of a blue line or the shore of a lake? And that's the second question. Those are really interesting questions. And how far upstream or how big of a water body do you draw, right, based on mean annual water body area? That's a tricky question. And so the second big one that we've run into again and again is kind of, what is this relationship between catchment features and water bodies? We clearly end catchments at the ocean, we end catchments at the Great Lakes, we end catchments at Lake Winnebago in Wisconsin, but we don't end catchments for smaller lakes and smaller water bodies, or even fairly wide rivers. The wide river flows through a catchment. We don't break the catchment network up. Well, we gotta tackle that. That's a data model problem that is not solved, and it's something that is going to take some work. So those are the two. I think those are the two biggest kind of like, wow, we have more work to do. But at the core of what we've done, I'm feeling really good about this kind of logical data model based on main stems and drainage basins. So I put in some material about the tool chain that's been developed along the way here that I just wanted to kind of mention briefly. If we have more time and people want to ask questions, I'm happy to go deeper into any of these topics. But my workflow is caveated up as provisional and in process, but it is available on GitHub. So I'll start at the bottom here. This thing I've been referring to as Mainstems is available as a repository. Bring this here. So all the R code, all the workflow stuff is here. It's runnable. It's available. Some of the diagrams or some of the graphics I used in this presentation are just in here as examples of the output of this workflow. Everything's implemented using a workflow tool called Drake. It's a kind of directed graph, reproducible data science workflow tool that's really nice. I'm really happy with it. Much of the reusable code that's been developed along the way of this work is actually in a package called NHD Plus Tools. So if you haven't come across this yet and you work in RSpatial at all, it is on CRAN, recently passed 2,000 downloads. So a number of people are using this. I'm pretty happy with how this has come together. Still kind of in a version 0 point something. I think I see a path to a version 1. There's some changes that I definitely want to make before this is something that I'm super happy with. But it's a great resource, something to be aware of, especially if you're working in the RSpatial world. And then the last thing is just, if you work in our spatial, I highly encourage you to check out our spatial. There's an ArcGIS bridge package if you want access to, or you need access to an Esri licensed set of capabilities. There's a good set of kind of ways to go back and forth between the two worlds, and it's a really impressive set of geospatial and kind of data science processing tools and visualization tools. Some of the mapping capabilities are really impressive. So, for example, with just one line of code in NHD Plus tools using R, you can get a map of the NHD Plus network, a drainage basin, and a nice little base map upstream of a stream gauge. This is all really simple, straightforward R capabilities. Much of this is work I did to get working in NHD Plus tools. But if you're not familiar with the R spatial world and some of the stuff that we can do in kind of these data science tool chains, I really encourage you to spend just a little bit of time Googling around and seeing what's out there, because it's really been transformative for my work. And I think in this day and age, writing a few lines of code is a really, really good thing to dig into, kind of regardless of what your role is day to day. So that is pretty much, that's what I had. I have a few more slides to get into more details, but I will stop there and open up for questions and kind of see where people want to take the conversation rather than going on any further. Thank you for your time. Thanks for listening. And if there are questions, I think you can unmute yourself.
I'm gonna.
I don't want to do that.
I don't want to unmute all. I'm gonna mute all again. Sorry. So yeah, in the participant panel of of the WebEx, you can. There's a little icon for your microphone. You can unmute yourself. If you called in and didn't put in your user code, then you're one of those call-in user number something. So does anyone have questions for Dave?
Yeah, this is Sean Vaughn from Minnesota.
Hi, Sean.
Good afternoon. I do have a question for David, and it's maybe not a question, but a few statements here. A lot of this work reflects what we've done here in Minnesota. I think any times we talk about these outlets and the correlation between an outlet and a main stem and why we have watersheds or catchments, drainage areas, if you will, that encompass lakes is because the history of our agencies mapping watersheds to meet a size criteria. I felt very strongly for quite a number of years that to overcome that, we really have to recognize that we should be parsing the landscape up by what we here in Minnesota ideally would call the hydrologic point of interest. So a lake outlet would be the pour point, and the pour point would be the indicator for the watershed drainage area upstream from that point. The other thing that we're losing here, just for something for the whole entire team to think about, something I brought up in past meetings and other venues as well, is the issue of scale. How we think about scale in the traditional sense, and in particular 1 to 24,000, is really changing. And we have to think about what is the role of LiDAR data and how does that relate to resolution. Here we see resolution becoming more of a definitive factor of scale, and then recognizing that LiDAR captures water conveyance landforms that then allow us to bring our delineations further up into the landscape, to be that all-encompassing drainage area system. So 2 key takeaways out of there is thinking about what is the role of LiDAR, and then what is the role and discussion around scale versus resolution for this type of work.
Yeah, great points. I couldn't agree with you more. And yeah, I think the part of the determination of what water bodies do you carve out of the landscape versus what water bodies do you keep kind of within your catchment network is what do you need a point of interest downstream of? Yeah. But then as soon as you zoom in and change the kind of fidelity of your data, that distinction might change, and it gets complicated. So, yeah, this is good stuff. It is great stuff to be looking at, and yeah.
Any other questions for Dave? So Dave, I'll throw one at you. So how, let's say I was interested in learning about R and coming at it completely fresh, where would I start?
Completely fresh. There are a number of really good resources. If you, I mean, I would point you to some of, if you just Google USGS R, there's some great introductory R training materials made available by USGS Water. From there, there's a fantastic book that's actually linked from the rspatial.org webpage. And there are a number of really good resources in this vein. So there's Spatial Data Science by Edzer and Roger, who are kind of two of the main leaders in this space. There's another spatial data science or geospatial processing in R. You just search for geospatial processing R book. It should come up. Yeah, this Robin Lovelace has this book called Geocomputation with R. That is fantastic. Between these two, you've got more resources than you probably know what to do with to get kind of into things. And the beauty of these books is they're written in R. They're written using Markdown, and if we look, down into some of the, so there are copy pastable examples throughout these resources. So I could copy and paste this directly into our studio, and things just run and work, and so you can use the examples directly. And that would be my other kind of thing, is like, just install our studio and start playing. And when you get an error, Google the error message and just play some more. If you didn't know, Googling the error message is 99% of programming.
Okay. Yeah, so I think, I don't know, maybe I'm speaking just from my own experience, or but I suspect there are a lot of people on our call here are pretty heavily in the Esri ecosystem, and haven't, I don't know, a lot of people I don't think have been exposed much to R, and maybe they're just not familiar. I certainly am not very familiar with it.
Yeah, so that there is an R bridge that's essentially, but my understanding of it is it's a similar tool chain to the Python package for ArcGIS, but in the R programming language. So that would be a place to start if you're familiar with ArcGIS and want to explore the R ecosystem. I know that it gives you direct access to the SF. So SF is a package in R that is kind of the bread and butter for doing this kind of work. So I know it gives you access to SF directly from ArcGIS data types. But this would be the other thing to take a look at, is the R bridge. One other thing I guess I would mention is if you can make it to the AWA Geospatial Technology Conference, there's a workshop the day before the conference starts on geospatial processing in R, where Mark, I'm blanking on Mark's last name. anyways, a gentleman from the EPA and I are going to be teaching a workshop on the day before the opening of the Geospatial Technology Conference is coming up in March, and there are plenty of other opportunities to get training on this kind of stuff.
Great. Any other questions?
Mark Weber, thank you.
You've stunned everyone, I think, Dave. Either that or
sorry. Somebody just raised a hand.
I'm going to try to unmute everyone here, just in case there's anybody desperately trying to say something. And yeah, just got the feedback. I think with that, we'll call it a day. I'm going to mute everybody again.